Okay, so the level of the atmosphere that we're walking around in right now, this level of the atmosphere, this layer of the atmosphere is called the troposphere. What are those little things? They're arrows, yes. They represent hot and cold, hot rising, cold sinking. There's going to be rotation or movement. Before it was in the earth, now it's of the air. We did put a name on them. Say it again. Convection currents. So we have convection currents that occur in the troposphere as well. And those convection currents that are in the troposphere, they create our weather. So that's the second part of my diagram. Rain, snow, thunderstorms. So the air in the troposphere is constantly churning. Hot air rises, cool air sinks. And that churning, those convection currents create our weather. Say that one more time. We are in the troposphere. Yes, yes. So this air that's around us is part of the layer called the troposphere. I know. It's amazing, isn't it? It's quite fabulous. So if you don't know what those little symbols are, the little pieces of popcorn, whatever, you might want to write weather next to it so that you know. But I recognize that as an amazing depiction of rain, snow, and thunderstorms. Right? I mean, it's like Picasso. The next layer, the layer above the troposphere, is called the stratosphere. And I have, before you listen to my melodious voice for just a minute, and I have a bunch of symbols in that layer. It is a capital O with a little subscript 3. Does anybody know what that means or what that's talking about? So the O is oxygen. 3 oxygen, whatever, yes. So the O3 means I have 3 oxygen atoms that are bonded together. Those 3 oxygen atoms that are bonded together create a specific molecule, and that molecule is called ozone. When you hear the word ozone, do you think good things or do you think bad things? Ozone layer is good. Ozone in the troposphere is bad. Down here, ozone is a pollutant, and it's bad for us, so we don't want it down here in the troposphere. The oxygen that we breathe is O2. What does that mean? 2 oxygen atoms bonded together. Well, O3 is 3, O2 is 2. Would seem that if you have 3 oxygen, it'd be better for you, right? The problem is the way that the ozone is bonded together, our bodies can't break that bond to utilize the oxygen. We need O2. If you do not breathe O2, you die. If you breathe O3, you die. So we have to have that specific type of molecule in order to survive. But ozone in the stratosphere is very important because it helps protect us from some of the sun's ultraviolet rays. So back in my day, when they had a hole in the ozone layer, there were people that ended up having more instances of skin cancer in places because they were more exposed to that ultraviolet radiation. So we want the ozone in the stratosphere. We just don't want it down here in the troposphere. And some of our combustion reactions end up accidentally producing it. So just put a whole bunch of O3 throughout that stratosphere to remind you that that's where it's found. That ozone layer in the stratosphere is formed naturally. It's a good thing. We want it there. The ozone that would be in the troposphere is a pollutant. It's man-made. It's not a good thing to have it down here. All right, so flip over to our ozone vocab. Please read for us the definition of ozone, Jordan. Energy. Yep. So UV energy, ultraviolet radiation, we want it to do that. We want it to absorb that. So let's make a little note for ourselves on the outside of that vocab sheet. So shut the door. And then on the outside, whoopsie doodles. So I've got it right next to my vocab. O3 is ozone. O2 is oxygen that we need to breathe. Thank you for reading out loud. And get you a highlighter. Highlight that, and then highlight ozone so that we know that that goes with our ozone vocab term. All right. Next layer, mesosphere. Okay, so hang on before you draw anything because it's not going to make a whole lot of sense just yet. So mesosphere is kind of the middle layer of the atmosphere, sort of like mesosphere, and the geosphere was kind of like the middle there, although technically we've only got 4 layers here, so it's kind of middle. So hang on before you draw anything there because I'm going to talk about the thermosphere. And hang on before you draw anything on the thermosphere, just listen to my melodious voice for just a moment. So thermosphere is the outermost layer. When you hear that word part thermo, what does that make you think of? Makes you think of heat, right? And so when we think of the outermost layers of the atmosphere, do we think it's hot out there? Do we really? I mean, it is. I mean, technically, it is. I just never associated with that, so y'all are smarter than I am. Because I always thought, it got colder and colder in every movie that you see. They're all, bundled up and stuff like that. But the thing is it's just that those molecules that are out there in that thermosphere, each molecule has tons of energy. So it in itself has a bunch of heat energy. The problem is they're so spread out that you don't feel that energy. It doesn't transfer it. The way a thermometer works is you take a thermometer and you put a thermometer into a substance. And when you put it into a substance, depending on how hot or cold that substance is, it's transferring its energy to that thermometer, the bulb where the alcohol or mercury is. Then that alcohol has the energy, and so it, we talked about those particles having lots of energy, and they spread out, and as it spreads out, the only way it can go is up, because that's where the little tube is for the mercury to go up, and that's where we take temperature. But it depends on them coming in contact with that molecules that have the energy and transferring that energy. So out in space where it does have a lot of energy, if you come into contact with those molecules, then it will transfer it to you, but they're just so spread out and so few and far between that it doesn't feel that a lot of heat and a lot of energy that's out there. It is the thermosphere, though, because it's out there where it can pick up a lot of energy from the sun. We have 2 parts of that thermosphere. We have the exosphere and the ionosphere. Ionosphere, ions, lots of little ionic particles. Have you ever seen or heard of the aurora borealis? Those guys are getting sun's radiation, and it makes them uncomfortable, so they have to give it off. So they absorb it, makes them uncomfortable, they give off that energy, and the only way they can give it off, the only form they can give it off in is in light. So that's why it glows, and that's why we have those aurora borealis. Exosphere, the outermost limits, that's where our satellites are rotating. That's where our satellites are at. Not revolving. Rotating? No, revolving. Revolving around the Earth because it's going around it. Rotating is in one spot. So that's where our satellites are at. So all of our phones, all of our technology that's beaming it up to the satellites, they're way out there in the exosphere. So one last thing. Hang on. Back to the mesosphere. As I'm moving from the thermosphere and the mesosphere, I just said that those particles out there in the thermosphere are few and far between and they're way spread out. The closer that we get to Earth, the more Earth's gravity is pulling on those particles and they're getting closer and closer together and it's becoming more dense. So any little piece of dust or trash or anything, a little asteroid, meteorite from space that comes through the thermosphere, the particles are too spread out for it to do anything, but once it's getting to these other layers right here, they're hitting a lot of those atoms in the atmosphere, and so it's causing friction. So I got a little piece of rock, dust, whatever, causing friction, and it can set it on fire if there's enough friction. So have you ever seen shooting stars? If you see a shooting star, chances are it's a piece of rock or dust or trash or something that's going through the mesosphere. It's getting pulled down to Earth, and it's going through a layer that's so dense that there's lots of friction, and it heats it up and can heat it up so much it catches fire. Now you can add to your beautiful diagram. So satellites are the furthest out in the exosphere. Those are my satellites. Ionosphere's kind of got a little green glow. Green, purple glow is your aurora borealis. These are where the ions are at. And then these are my shooting stars that are going through from outer space through that mesosphere where it's much more dense. Let me go make sure everything's okay. All good? Questions? Satellites in the exosphere. Ionosphere is at the bottom of the thermosphere. All right. Speaking of the atmosphere, there are two gases that make up most of the atmosphere. What's one of the two gases? I hope it's oxygen because we need that. Carbon dioxide gets a really bad rap. It's a very small percentage, and that's one of the reasons why it gets such a bad rap is because if it's such a small percentage, let's say it's 1%, it's less than 1%, but let's say it's 1%, and it goes up to 2%, well, that's doubling the amount of carbon dioxide, and that's why it gets so much notability is the fact that just a little increase ends up being a big increase for the atmosphere itself. So carbon dioxide is a component, but it's within a percentage less than 1%. What else? Nitrogen is the other big one. Nitrogen is not something that we can breathe, and in fact, we can't really utilize it in the gas form except in your tires, but that's an entirely different story. But in terms of forms of life, it has to be kind of processed in order to be used by plants so we can get it from plants to use it in our bodies, and we'll look at that in a week or two when we look at the nitrogen cycle. But oxygen obviously is the big one. So which one is more in our atmosphere, oxygen or nitrogen? We would think so, right? But it's nitrogen. Nitrogen is much more than oxygen in our atmosphere. So this is on the outside of our atmosphere vocab. Our atmosphere is 78% nitrogen, 21% oxygen, that's 99%, and so it's 1% everything else. Carbon dioxide, hydrogen, carbon monoxide, ozone, pollen, water vapor. 78% nitrogen, 21% oxygen. When we do our nitrogen cycle information, we'll find out that that 78% nitrogen is basically naturally formed. But where do we get oxygen from? Plants, trees, pardon? Moss, anything green. Those plants and vegetation that get all the credit. But they don't produce most of the oxygen that we have. Bacteria, that's photosynthetic. Did you say bacteria? Sorry, you gotta say it louder. You're way over there, I didn't hear you. Bacteria that's photosynthetic, critters that live in the ocean, algae, stuff like that, and then the cyanobacteria that lives in the ocean, those make up most of the oxygen that we have, which makes sense because the earth is covered with 3/4 water and only 1/4, dry land. So plants are totally outnumbered by things that live in the ocean. All right, so that's what we saved a little bit of room at the bottom of our notebook for. The key is photosynthesis. If it is something that goes through photosynthesis, it's producing oxygen for our atmosphere. So oxygen in the atmosphere is produced by plants, algae, bacteria, anything that goes through photosynthesis. Then whatever color you highlighted atmosphere, make sure you highlight that too so that you remember that those go together. So this is information that goes with atmosphere. All right, so we know that these layers right here are the geosphere. We know that these layers are the atmosphere. We talked about biosphere before. Does anybody remember what biosphere is or what it means? What does bio mean? Living or life. So biosphere is the part of the earth where living things can exist. So atmosphere, gas, geosphere, solid part of the earth. We haven't done it yet. Hydrosphere, what do you think? Water, hydrosphere, water. Bio, life, so biosphere is where the living things can be. And so I had you leave a little bit of room on the side. And so lithosphere, asthenosphere, mesosphere, outer core, inner core is our geosphere. Troposphere, stratosphere, mesosphere, thermosphere is our atmosphere. The biosphere, the living things can be down in the crust. Remember, we got worms, things that burrow, bacteria, stuff down there. And we've got stuff that can live up in the atmosphere. So I've made this so it kind of overlaps both the geosphere and the atmosphere. So biosphere within the ground, on the top surface of the ground, in the atmosphere, those are the places where living things are found. I'd give you a headache. I mean, you can sit right there if you want. I bet Tiffany would let you borrow part of that desk over there if you need to. That's fine, so long as you get the information. So biosphere within the ground, on the top of the surface, and in the atmosphere. It's the place where living things are found. When we talked about the layers of the Earth and the geosphere, we talked about the atmospheric pressures and how many atmospheric pressures that was all the way down there in the core. So one of the things that's and then talking about the mesospheres and the fact that the shooting stars occur there because they're burning up there. So one of the characteristics of the atmosphere as a whole is as you get closer to the surface, there's more pressure. As you get further out, there's less pressure. So whenever I think of the atmosphere, I always think of it as like one of those little human pyramids. You know, I'm talking about little cheerleaders, human pyramids. They all standing on each other's backs. Who do you think is the happiest in that human pyramid? Because they don't have a lot of pressure on them. The person at the top is probably the happiest because they don't have anybody on their back. Who's feeling the most pressure? One's at the bottom because they're feeling the pressure of everybody on top of them. And so if you look at each person as being like a molecule, that kind of represents what happens as you get closer to the surface of the Earth. There are much more molecules of gas, atmospheric, whatever, down here than there are all the way out there in the thermosphere. And we feel that. We just don't notice that pressure because we've been with that pressure all the time and we're used to it. So have you ever been up in a plane and felt the lack of pressure? Pressurize that cabin, but then your ears pop or don't pop or whatever. There was one time I had a water bottle in there, and the water bottle, as we went back down to it, because I took a drink, then as we came back down, it all got squished up because it's feeling all that extra pressure that it didn't before. So, I mean, it's there. It's just not as obvious because we're used to it when we're here. So that's what our two little Post-it notes are for. And notice that I have these Post-it notes stopping right there at the troposphere, because this is just dealing with the atmosphere and atmospheric pressure. So here's my little human pyramid of molecules, if you will, and the folks on the bottom, they're real upset because there's so much pressure there. It's much more dense closer to the surface of the Earth. It's much less dense the further out that you go. The reason why we have an atmosphere is because our gravity is holding those molecules to the surface of the Earth. When you think of places out in space that don't have an atmosphere, one of the reasons they don't is because they lack that gravitational pull to hold stuff to the surface. Sorry. I apologize for offending you. I mean, those are two different concepts. You can have gravity and still have a flat Earth. Oh, that's okay. My mistake. I missed that part. So it's more like centripetal force rather than gravity. Gotcha. Oh, I can. Yeah, thank you. I appreciate that. Hmm. I know, and I tighten it, but it still squeaks. Yeah, I think the only thing that's going to fix it is a sledgehammer. Yeah. I know. All right, so before we leave this page, let's go ahead and define hydrosphere. Read the definition of hydrosphere for me, please, Lexi. All right, and so hydro, we put two and two together, water, and so that's the water that's on the Earth. And one last one for today, tectonic plate. Please read for us the definition of tectonic plate. Riley. Asthenosphere. Lots of big words in that one for you, right? Large pieces of lithosphere, large pieces of crust that move around because of the asthenosphere. So remember, we said that those convection currents in the asthenosphere were kind of like the wheels on our little conveyor belt. Whatever direction they're turning, they're going to move that crust around on them in that direction. So I gave you a picture. And we want to turn to the next two pages. So this is where we're at. This is where we're at. So turn to the next two pages, and on the top right-hand side, if you would please go ahead and tape in your picture of the lithosphere. And notice, I mean, my OCD required me to put it this way. We've got stuff that we need to put underneath here. So make sure you push it all the way to the top, and then just put it to where you can fold it in. One piece of tape on the fold, one piece of tape on that corner right there works really well. Thank you for reading. Thank you for reading. So the little black lines represent the boundaries of those plates, of those pieces of crust. The thing is that the asthenosphere underneath it isn't all moving in one direction. It depends on that particular set of convection currents in that area at that time as to where it's moving. Oh, and I forgot about that, but we'll talk about that later. So just a general idea of how things are moving. We're just going to add some arrows to it. So this entire plate over here, in general, is moving in that direction. It's moving from, well, it's moving in that direction. I'm just going to leave it right there. But this little chunk right here is moving up towards Europe. And so that's why there's a little sea that's kind of opening up in this area right here, because those pieces of crust are allowing water in as it's moving. India is being slammed up into Asia. The highest mountains on Earth are found in this area. That's because those plates are slamming into each other, and that oceanic crust can get flipped underneath, but we've got two pieces of continental crust. So they can't flip down underneath it. So when they're going into each other, all they're doing is crumpling up and forming those big mountains there. So, yeah. All right, and so Australia's kind of the same way here. But this piece right here is moving a little bit more in that direction. That's probably your problem. This is Mrs. Johnson. No, she'll be in math right now with Mrs. Haas. Alrighty, bye. I thought it was, but I guess not. And so all of that movement in that general direction. So Japan, those string of islands right here, what we got going on here? This guy too, right? Yep. This guy too, right here. Lots of earthquake activity in that area. This whole Pacific plate is kind of really mad at the stuff to the west of it. And it's kind of moving in that direction. There's a little bit of a spin to it. About 2 centimeters a year, I think, is what they've clocked our tectonic plates moving. It depends. It depends, once again, is there any friction to it? You know, are they running into something? Is it able to subduct easily? North American plate, kind of moving in this direction right here. We have a transform boundary there in California, and so it's sliding past each other. But California is not going to like drop off into the ocean. We have continental crust that's underneath there that doesn't allow it to just fall, the whole state to just fall off. Now it can get eaten away by the ocean little by little, but it'll still be there underneath the water. We have lots of volcanic and earthquake activity that happens over here, and that's because these plates are going head to head in opposite directions. The fact that there is so much conflict between those plates has created a phenomenon called the Ring of Fire. Sure, you can make it orange, whatever you need. Just to indicate the fact where we have lots of earthquake and volcanic activity because we have lots of interaction between those plates. So one last thing. We need to go ahead and define that Ring of Fire. The area around the Pacific Ocean where colliding plates create numerous volcanoes and earthquakes. Ring of Fire is the area around the Pacific Ocean where colliding plates create numerous volcanoes and earthquakes.